So let's take a look at these two questions that we didn't have time to finish in class. Number 3 here, again, we're just determining the intersection for, and we're given our three equations for our three planes. So I'm just going to label these plane 1, plane 2, and plane 3. And as always, the first thing we want to do is we want to look at our normals. So our normal for our first plane is 1, 3, 5. The normal for our second plane is going to be 2, 6, 10. The normal for our third plane is going to be 1, 3, 5. Okay, so first thing we can see right away is that obviously plane 1 and plane 3 are going to be definitely parallel because they actually have the same normal there. And normal 2 here is a scalar multiple of normal 1 or normal 3 there. So all three planes are parallel. So once we've established that all three of our planes are parallel, we have to decide, are all three of them parallel and distinct? Are two of them coincident and the third one distinct? Or are all three of them coincident? So let's take a look at how we could try this here. One thing we could try here is we could start sort of solving the system here. And if I try to solve like by eliminating a variable here. So if I take plane 1 and I subtract plane 3, what's going to happen here? Well, I'm going to get x minus x is going to give me 0x. 3y minus 3y gives me 0y. 5z minus 5z is going to give me 0z. And then 10 minus 9 is going to give me 1. So I end up with 0 equals 1. Okay? This is never true. So we know that our system cannot have a solution. So our system is going to be inconsistent. Okay? So there's no solution to our system, and we know for sure that 1 and 3, these two that we've been looking at, therefore pi 1 and pi 3 are parallel and distinct. Plus distinct. Now, what about plane number 2 here? Well, if we look at the equations for plane 2 and let's say plane 1, we can see that, plane 2 and plane 1, we want to check to see if these planes are scalar multiples of each other. So the two we want to look at here are plane 2 and plane 3. Because if we take the equation for plane 3 and multiply it by 2, we get the equation for plane 1. 2 times 1 gives us 2, 2 times 3 gives us 6, 2 times 5 gives us 10, 2 times 9 gives us 8. So these two planes are scalar multiples, therefore they are coincident. Okay. So we know now that our system has two planes that are coincident, plane 2 and plane 3, and the third plane, plane 1, is parallel and distinct. And we already knew that our system was inconsistent. So that's all we really need to do here to answer this question. Two planes that are coincident, two planes that are parallel and distinct. Okay, let's take a look at the last example here. This is question number 4. We want to determine, again, the intersection for our three planes here, and I'm going to start just, again, by labeling them plane 1, plane 2, plane 3. Again, we want to look at our normals. Normal 1 is going to be 1, 1, negative 1. Normal 2 is going to be 2, 2, negative 4. And then normal 3 is going to be 1, 1, negative 2. So what do we notice when we look at our normals? Well, we notice that 2 and 3 are scalar multiples. So these guys are going to be parallel. Okay, plane 2 and plane 3 are parallel. And if we look at the scalar equations, we can see that, again, the equation of plane 2 is a scalar multiple of the equation of plane 3. So plane 2 and plane 3 are coincident. We go back to our normals here. We see that normal 1 is not parallel to the other two. So we have, well, that's two L's there in parallel. Let's fix that. So we know that two of our planes are coincident. One of them must come in and intersect the other two. Okay? So what we want to find now is these are going to intersect in a line. We're going to have that one line where our non-parallel plane intersects our other two. So we want to find, we know that there's going to be a line of intersection. Between, we could either pick plane, it's definitely going to be plane 1, that's our non-parallel one, and we can pick either plane 2 or plane 3. So let's find the intersection between plane 1 and plane 3 at this point. So the way we proceed is the same way we did all those questions where we were finding the intersection of two planes. Okay. We can eliminate one variable from our original system here. So I'm going to choose to eliminate x from equation 1 and equation 3. And I'm going to choose x because it looks pretty easy. We're just going to do pi 1 minus pi 3. And when we do that, what we notice is that our x's are going to cancel, our y's are going to disappear as well, and we're just going to be left with z components. So we're going to have negative z minus negative 2z, so that's just going to give us a positive z. And if we do 5 minus 3, that's going to give us 2. So the first relationship we have is z equals 2. Now remember, what we're going for here is we are going for our parametric equation of this line. We need expressions for x, for y, and for z. So we've got our z expression. We need our expression for y and our expression for x. Well, we can go back and we can eliminate. We've got our expression for z, so we can eliminate z from one of our original equations. So let's fix that. Eliminate z from, I'm going to eliminate it from pi 1, and I'm going to do this by substitution. Basically, I have a value for z, which I just found, so I'm just going to sub this value for z into my equation pi 1. So pi 1 is going to become x plus y minus 2, that z value, equals 5. Then I can take this expression and rearrange it for either x or y. So let's rearrange this. For x, we are going to get, bring that 2 to the other side gives us 7. 7 minus y. There we've got our x expression over here. So all we need now is an expression for y. So we can always choose one of our variables to be our parameter. So we're going to choose y equals t. Okay. So our parametric equations are going to be x equals 7 minus t, y equals t, and z equals 2. Or if we wanted this as a vector equation here, our vector would be, let's see, 7, 0, 0, oh, 7, 0, 2, sorry, plus t times negative 1, 1, and 0 would be our line of intersection. Okay. So we can sum all this up. The system is consistent because we found a solution, dependent because we found infinitely many solutions, and we've got our line of intersection up there. So we are done.